I'm Nick Weaver, a researcher at at ICSI, which is a UC Berkeley affiliated research lab. The way to put our position is we get at berkeley.edu email address, but we're actually independent of the regents. And this is joint work with Christian, Boris, and Vern. And it's results of a network diagnostic and debugging tool that your mother can run and send you the results, and you'll actually be able to understand, hopefully, as well as a general survey. So it's basically, the problem is network transparency and network debugging, and we wanted something that we could run ourselves whenever we get to an oddball hotel network to know just the internet is broken, but we'd like to know how it's broken. And so it's basically, it's all in Java and JavaScript. Java within the same origin policy. You can do arbitrary TCP and most of the time UDP. You can look up arbitrary DNSA records, but it will only return either the host or a security exception. And if the user happily clicks on the I accept this signature button, and we know users happily click on that, we can bypass same origin completely. And then JavaScript can do cool stuff. And our servers can do whatever they want too. And so it basically works like this. The user visits our web page, clicks the Start Analysis button. A Java signature may or may not come up depending on if they've run it before. And it goes and runs through a whole battery of tests that are rather boring results when run on this network, because this network actually works. So let's look at a network that didn't work in order to see what it does. This was from vacationing in New Zealand and gives you an idea of the test suite involved. So to start with, NAT. Is it NATed? Yes, it is, but ports are not renumbered. Is it on any interesting blacklists? No. What's the outbound connectivity? Oh, cool, it doesn't block anything. Quite unusual for a hotel. What about UDP? Well, can't send fragmented UDP because, well, the NAT is broken or some firewall is broken. But it can receive fragmented UDP. What's the path MTU? Path MTU is 1480. Oh, and it actually gives me an ICMP too big. Oh, that's friendly. That's less common than we'd like. Latency to our server, we use EC2, so it's East Coast US, so from New Zealand, it's slow. Bandwidth, buffer capacity. A lot of end users have these access devices that have horribly large TCP buffers. This is why BitTorrent kills your net. Are there hidden HTTP proxies? Oh, yes, there is. It's changing the capitalization on stuff. Oh, and it's vulnerable to a rather nasty bug. If you have anybody you know running Blue Coat, have them run Netalyzr. There's probably this vulnerability is in a lot of Blue Coat stuff. Is there an HTTP cache? Yes, there is. Does it work right? No, it doesn't. Fortunately, HTTP caches are rare. Unfortunately, when they do exist, they cache data they aren't supposed to. Is it V6 capable? DNS behavior, DNS properties, DNS glue policy. Oh, and we even check the clock. Now, let's actually discuss some of the results that we see. So it goes front end, back end. So we've got a nice big test suite. We released beta summer '09. We have a non-beta release January 2010 where we added a lot more tests. And we've had 110,000 unique sessions so far, and it continues to trickle in. And the results I'm going to talk about is basically for a year's worth of data. There are biases in our data set. Geeks like this tool. We can tell because a lot of people are running OpenDNS when they use Netalyzr, and I don't think OpenDNS is 10% plus of all users on the internet. NAT, obvious. 90% of the sessions are behind NAT. NATs are ubiquitous. No big surprise. Most NATs, about 2/3 of them have a DNS proxy in them. So they will respond to DNS requests, because this is how they are able to give out a DNS server before they get their own DHCP lease. About 4.4%, 4 or 5% of the NATs will respond to external DNS requests. There are a lot of DNS reflectors out there. Protocol filtering tests connect to an echo server that is deliberately not any other protocol. So anything that's protocol sensitive, we'll see that and kill it, so we can detect proxies and firewalls. Some surprises. Local POP proxies are very common. Often this is on the host itself, AV shimming itself into the network stack. NATs include FTP proxies, quite common, and most of these proxies don't like our communication. SIP awareness is actually quite common. We've had several cases now of network admins going, no, we aren't doing anything to SIP in our network. Oh, wait, random foozy-wox at XYZ in the middle of the network actually implements SIP-aware logic and terminates stuff that isn't SIP. We were surprised by how little outbound SMTP filtering there is. It seems major ISPs are doing dynamic blocking these days of SMTP rather than static blocking. Expected, run your SSH server on port 443. If there's one port that's not molested, it's that one. And, of course, the Windows port blocks are very common. And slammer blocks, the 1434 UDP, I believe it is, quite ubiquitous. A lot of people turned on blocks, 7 years ago, that never got turned off. So there's a UDP port that just doesn't work. The DNS, we actually check for DNS awareness by communicating directly to our server with DNS and non-DNS traffic. About 11% of sessions reject non-DNS over DNS. So if you think you're going to be clever and tunnel your stuff over DNS, make sure it looks like DNS. Proxies, however, are rare. Mostly this is hotel networks where they'll have a captive DNS proxy. We're able to see those. We also check whether we can get large responses. Unfortunately, a bad bit of news. About 1.3% of sessions can't handle eDNS at all. About 5% fail the ability to handle DNS requests larger than 512 bytes. There's a lot of old firewalls out there. And another additional 10% can't handle fragmented traffic. This is a problem if you want to do DNSSEC validation on the client. Unfortunately, we'll see in a sec, that's also problematic from the server side. So we're able to fingerprint DNS resolvers based on glue policy. A lot of bind out there, or at least bind's default policies. This is a problem. About 10% of the DNS resolvers that advertise the ability to receive large responses can't, because they're behind some firewall that can't handle fragments. This is worrisome for DNSSEC because people are going to want to push larger and larger amounts of data, and you can easily start kissing that UDP fragmentation limit. DNS wildcarding is unfortunately growing very common. This is that stupid helpful service. And there's sort of three ways to do it that we've observed. You have wildcard everything that's www. Offenders include Comcast and Verizon. There's wildcard everything, which is like Charter and Quest. This causes more collateral damage. And there are some which currently wildcard serve fail. But so basically, 28% show wildcarding. If we exclude Comcast, we exclude OpenDNS, it's still 20% show wildcarding. So anybody who's relying on DNS returning errors in erroneous situations can't anymore. Too bad you have trouble with DNSSEC on the client. We look up a large number of names on the client, send them to the server. Server does reverse lookups. We see 3 interesting strains of games being played. Well, there's beyond DNS's use as policy, that's now accepted, it seems. But you have OpenDNS is a proxy for Google. They do tell you about this, but it's in order to turn it off, you have to turn off other features. Wide Open West and a couple other ISPs, at least were during our initial run, man in the middle and Google, using DNS to point to a proxy that they control. If anybody has any information about what these proxies are supposed to do, I'd love to hear it, because I don't know. And the real fun one is there are malicious DNS resolvers that people's malcode will set people's DNS settings to. The fun part is they'll redirect ad.doubleclick.net to point to a server that serves up ads for Vimax mail enhancement product. Hey, it makes them money. And all these problems are due to the recursive resolver, which means you have to do DNSSEC validation on the end client. You can't trust the recursive resolver, but the end clients are going to have trouble actually being able to receive the data necessary to do DNSSEC validation on the client. It's a problem. Fragments don't work. Everybody knows this. We have the data that says so. One thing that is a problem is you do have systems that can send fragments, but have an MTU hole at 1499 bytes. The common cause for this is Linux sets DF on UDP packets, and then what happens is the packet either gets dropped silently or an ICMP comes back that's sent back up through the application stack to the application that then treats it as an exception and terminates the connection. Yeah. And the only way you can turn this off under Linux is turn off all path MTU discovery, not just UDP path MTU discovery. So this is a problem we see. The network is mostly, but not all, Ethernet. We saw really 13%, a surprising amount of PPP over Ethernet. Or at least we infer it's PPP over Ethernet because it's the 1492 MTU and it's associated with DSL providers, not cable providers. ICMP 2 bigs are unreliable in v4. Only 60% or so of the cases where we should have gotten an ICMP 2 big, did we? And so the conventional wisdom is correct. The network has decreed for us that fragmentation doesn't work, and that path MTU discovery must use fallbacks because the ICMPs are unreliable. And HTTP proxies, about 8 to 9%, commonly in hotspots and corporate networks. This is how a lot of corporate censorship is done. When you're going through a proxy, it's commonly a mandatory proxy. As I said, when there's in-path caches, they're wrong, but they're rare. We only see about 5% in-path caches. Transcoding, people have talked about it, but we don't see very much of it where the image is changed by the network. Also, everybody probably wants to know IPv6. Well, we don't have IPv6 on our systems yet, but Google does, so we load the IPv6.google.com image in a hidden div and report the status back. We have a geek bias, and so about 4.5% of our users were able to fetch IPv6.google.com. So IPv6 is starting to get out there, but it's still pretty slow adoption. So the big reason why I'm here is I want to know what your questions are. Netalyzr is an ongoing project. We are continually doing enhancements, and we want to know what other people want to know about how the network is broken. So I've been talking with some of you offline about IPv6 issues. If you have concerns, what you think is going to break, please tell me. Also, it actually works. We are able to pull this off, do a large, wide-scale measurement, and you know you built it right when your measurement applet hits /dot and sysadmin asks, so when you're getting on /dot, and your answer is an hour ago. If you have other questions, there is also a tech report available I can email to people. Questions.
Brandon Ross, Subspace, StoryPoint. You kind of alluded to it a little bit in the presentation about different brokenness by region or by type of provider or something like that. That kind of data would be very interesting from a, I don't know, maybe a research point of view, but also what am I expecting to deal with in this part of the world or in this type of provider kind of point of view. So.
Excellent suggestion. We do have, like, for ISPs, we have a top 10 things. So, like, a couple of which major ISP still has the slammer block? That's in the tech report. How different ISPs are doing wildcarding. Who still has PPP over Ethernet? So we do have a lot of that in the tech report already. And we don't want to release our data because there's potentially privacy-sensitive data on people's network policy. But if you can come up with questions you have about the data, we can probably construct database queries to answer those.
Yeah. So in the report, do you do any regionalized reporting? Do you say, you know, there's more slammer blocking in North America?
Not yet. In terms of breaking apart across country, we do our bandwidth. We did that as much as a sanity check because you can get a feel for things that way. We haven't looked at things like slammer blocks across country versus across ISPs.
Right, or content filtering, for example, can really be an interesting metric too.
Most of the content filtering we see is corporate network content filtering.